Hey y'all, for this month's rebroadcast, we're going to revisit our episode on snowflakes. We picked this episode because I love the wintry vibe, and also we're going to be talking a little bit about evergreen trees next week.
Nice. We won't be having snow quite yet here down in Texas, unfortunately.
Hey, we can dream.
We could dream, but a lot of you guys might be already.
Right.
So who knows? Whatever. It's fine.
So that's why we picked this fun wintry themed episode, and we'll see you back here next week with an episode about what Christmas trees and jet fuel have in common.
Whoa, nice. This one's super interesting. Enjoy it. Happy listening. See you guys soon.
Hey, I'm Melissa.
And I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast helps you understand the chemistry of your everyday life.
Okay, today is our first episode of winter.
Oh, really?
Officially. Yes, winter starts December 20th.
Uh-huh.
And this is the first episode that's coming out since then.
Dang, interesting. It's weird because, it's not always really, really winter in Texas yet, but whatever.
It's not even, it's like winter for 2 days and then it goes away and then it comes back starting in October.
Yeah. Interesting.
But winter officially begins December 20th.
Nice.
And this is our winter spectacular.
Nice. So we have like a wintry theme.
Yeah, we're going to learn about the chemistry of snowflakes.
Oh, nice.
So snowflakes are actually something called crystals.
Whoa. But okay, interesting.
We've talked about crystals before.
I just always thought of it more like in the rock category, like crystals meaning more like minerals or whatever.
But they're not. Crystals are known as highly ordered substances. They're usually in a solid form because they are highly ordered.
Okay.
Snowflakes is frozen water, so it is technically a solid.
Uh-huh.
So another example of that you've probably seen is rock candy.
Okay, yep.
If you ever grew that rock candy, those are crystals.
Mm-hmm.
And then, beautiful gemstones and stuff are also crystals.
That already seems interesting because I don't think of those things as like frozen. I just think of them as solids, things that have grown or whatever, like mineral. But thinking of a snowflake as that is weird because I've always had it just in the category of like ice. Like, oh yeah, it's just frozen water.
Frozen water is solid water.
Right. But the idea of it being like a crystal just seems weird.
But everything that is solid has technically been frozen. It's just that its melting point is well above room temperature. Some things, quote, freeze at 75 degrees Fahrenheit room temperature, and that's why they're solid. Coconut oil, it has a weird melting point somewhere right around room temperature. So if you have a warmer house, it's meltier.
Yeah.
If you have a cooler house, it's more solid.
Right, which you talked about in the magic shell discussion.
But we call that the melting point and not the freezing point because we'll talk about things can get super cooled and not hardened.
Mm-hmm.
But things always melt at the same temperature.
Interesting. Weird.
Your mind's kind of blown by something that I wasn't even planning on talking about.
Well, just that, not like I knew that everything had different points of melting or freezing or whatever, but I didn't think about how things that are just objects like this table is frozen.
In a way. Yeah.
That is weird. Okay, so snowflakes are crystals.
They're crystals. And I think this is true for every topic, but I am acutely aware for this topic of how much I don't know. That might be because I know a little bit more about it than some of the other topics, but there are people whose whole jobs is to study crystals.
Mm-hmm.
So there's a lot about growing crystals and crystalline solids and stuff that I don't know, but I do still know quite a bit, and that's what we're going to talk about today.
The people who study crystals, they use them to keep spirits away and stuff like that, right?
I think that's a different type of crystal.
Okay.
But we'll talk about the people who study crystal in labs at the end of today's episode.
Okay. All right.
There's a really cool thing that happened while I was looking stuff up for this, so I'll tell you about it.
Okay. I'm ready.
So if I've made a new compound and the majority of that compound is pure, like I have a pile of something, the way that we use that is hot liquid has more solubility, more capable of dissolving things than a cool liquid. You've seen this when you've tried to dissolve your sugar in iced tea
Right.
versus when you get sweet tea.
You're right.
If you dissolve it in the water that's already cold or the tea that's already cold,
Yeah.
it doesn't really dissolve.
And you brew tea hot, and so most people will add the sugar then.
And then it goes in just fine.
Yeah.
So we use that concept with crystal formation to purify substances. So if I have a pile of something in the lab and I know it's mostly that thing, and I need to just get it perfectly pure before I can react it forward to the next reaction, I'll put it in, usually it's not water, but we'll just say water.
Mm-hmm.
And it won't all dissolve at water at room temperature, but I heat it up and then it starts to dissolve in the water as it's warm.
Uh-huh.
So it all goes, we call it going into solution. It's all dissolved in the solution. You have a nice mixture of your liquid, in this case water, and whatever your solid is. So it's all a liquid solution. And as it cools down, because it's not soluble at room temperature, it starts to come out of the solution as a solid. And it will form very ordered patterns known as crystals. Because it's slowly cooling down and slowly things are coming out and they have the opportunity to just build up that crystalline structure.
And then the other things in it that were like impurities or whatever, do those things not form as part of the crystalline structure?
Because they can't take that same order shape. They're not the same shape.
Stay in the water or whatever you used as a solution.
Mm-hmm. Yeah.
Interesting. Because you mentioned that with your friend, Dr. Who, made those crystals.
Yes.
You talked just a little bit about this, but I was still not getting where the impurities go. But now it makes sense. There's no place for them. They can't form
into that highly ordered thing. Yeah. And that some of getting into that is pretty complicated of why does nature form very highly ordered patterns naturally? And why would that impurity not go in? I don't think that's super useful for us to talk about now, but now you kind of know the basics of what we use growing crystals for. And then we have this nice pure substance. And if you can get one single crystal, they can take an Xray of it.
Mm-hmm.
And those are people who study crystals. The person who takes an Xray, they're people who study crystals. And we're going to talk more about them at the end.
And they can figure out like which ghosts and spirits that crystal can.
Actually, what they figure out is I'll give you a little preview. They're called X-ray crystallographers, and they send in the X-rays and they measure the diffraction of the X-rays or the way that the X-rays bounce off of the particles. And based on that, they can figure out the molecular structure of what's inside the crystal and how they're stacking on top of each other.
Interesting.
So in some of the work I did, I was able to grow a crystal. And so there is an X-ray that shows the exact structure of the atoms and the way that each molecule is lying on top of each other. And they can prove that with an X-ray.
Wow.
Isn't that so cool?
That is crazy.
So that's some of the benefit of growing crystals. You have incredibly pure substances, but also you're able to study the molecular level with a crystal. That you can't do the same thing if you just have a bunch of powder of it. It's not going to be the same highly ordered material.
Yeah.
So that's what we do in the lab when we're trying to purify crystals. But you might be wondering, what does that have to do with snowflakes?
Yeah, it's like who up there in the sky is trying to purify water and make crystals out of it in the wintertime?
I don't think anyone is up there. Little elves that are like, we've got to get our perfectly pure water. And then it falls down to the earth every time and they get sad. I just have that image in my head. There is a concept in forming crystals where your substance, for some reason, won't come out of the solution and form those solid crystalline materials unless it has something to latch onto. So usually it's the glass walls of the container. But if it doesn't, you can scratch those and the crystals will just form like magic. It's insane. What? And you've seen something like that because people will super cool water.
Oh, yeah, I've done that.
And then as soon as you put the ice in, boom, it freezes. The whole thing. That same concept happens with crystalline formation of solids.
The way I've done that before was I would have the bottle of water right next to the cooling element of the fridge.
Mm-hmm.
And then I'd take it out very gently and then smack the bottom really hard.
Mm-hmm.
And it would go.
Yep.
And become solid.
Yeah.
Frozen.
So the same thing happens with crystals. My
Okay.
students.
Weird. Interesting. I just did not think that those things would have linked in some way.
Mm-hmm. I mean, water is forming crystals too. So it's very, very similar. My students love that. There's this one lab they had to do where they're supposed to make crystals. It's like a second year college student activity. And without fail, every year there's someone who theirs just doesn't go. And then I take it and just gently scratch the side, like scrape it very gently with another piece of glass, like a glass rod. And it just goes.
That's crazy.
Like, well, how did you do that?
That's so crazy. I'd love to see that.
It's really fun.
So you're telling me you expect me to believe that when I drink a bottle of water, I'm just drinking a bunch of dissolved snowflakes?
I mean, I don't know if they were ever snowflakes, but probably yes.
What?
Okay, so
New York Times has got to hear about this.
Okay, so snowflakes they're crystals and they form around dust or pollen because they need something to latch onto.
Oh, that is interesting.
Mm-hmm.
What?
And they'll start to group around it, the water molecules. And do you remember that water has hydrogen bonding?
Yes, because each molecule is one hydrogen and two oxygens.
Mm-hmm. So when they're coming together towards each other, the oxygens and the hydrogens will sort of line up. And because of that, the snowflakes form that hexagon shape that we're used to seeing.
Oh, yeah.
Mm-hmm. The molecules have to form a hexagonal shape so that they are arranged so that the oxygens and the hydrogens are lining up. That's why snowflakes are hexagonal.
Interesting.
It is impossible to have an octagonal, to have an 8-sided snowflake in the Earth's atmosphere.
Wow, that's weird.
Water can take other forms that aren't hexagonal structures, but they won't do that naturally in our atmospheric conditions. They would have to be under different temperature and pressure conditions to make them form different structures.
Interesting.
And there is a lot of studies about there's all these different types of ice, but I haven't learned a ton about that because I'm more interested in other things.
Yeah.
That's 8-sided snowflakes that you see when you decorate your house. I literally have some at home. So, everyone scour your house, and if you have 8-sided snowflakes, get rid of them.
Yeah.
They can, though. Snowflakes can have 12 sides.
So it has to be
because it's a multiple of 6.
Got it.
But I think that's very rare. I've never seen it. Essentially, the dust pollen starts the snowflake and makes this hexagonal pattern of water molecules. And remember, the flake is moving around through the air. And the air has water molecules in it also. And so as it's moving around through the air, more molecules are going to attach onto them. So they're attaching from, the 6 sides. So that's why they have their 6 arms. And depending on the temperature, how many water molecules are in the air, all that stuff, it will deposit at different rates and in different patterns. So if it's faster, they're going to stack up on top of each other more. They're depositing in quick succession. That's why you have your long, skinny parts. And then things can grow out from there if they're encountering more, if maybe it's warmer or cooler. And that's why they say it's nearly impossible to have 2 snowflakes that look exactly the same or that are exactly the same on the molecular level.
Yeah.
Because it's nearly impossible to recreate the exact same conditions of when a snowflake that's forming is going to interact with another water molecule, if it's the right temperature, how quickly it'll have another one come on after that. They're swirling around in the air. I mean, it is nearly impossible to have the exact same snowflake.
That makes sense.
Especially if you zoom into the molecular level, even if they look the same to the human eye.
I didn't think about the pattern that would form the snowflake itself. I just always thought about like how that could be true about anything. Like you're not going to find 2 the exact same blade of grass, even though it's a grown thing or whatever. You're never going to be able to find 2 that are like perfectly the same. In my mind, it was just like a truth about nature, but I didn't think about the fact that like
why,
because it's an overtime thing. It's like there's this phase of more water molecules, happening faster as it's falling, slower, faster, slower, faster. It just wouldn't have.
Warmer, cooler, warmer, cooler.
Yeah. Yeah.
Mm-hmm.
Interesting.
So that's it. That's how snowflakes form.
Interesting.
They're crystals that are growing as they fall through the air.
Which makes sense because they're falling through the air, which allows them to kind of like form in these different directions, and they're falling around all these other water molecules, which allow them to like get bigger. Yep. But we see like frost form, and there's some similar
patterns,
but it's not as it's not the same, and it isn't like detachable really. Frost on something is like on there, like you can't just get it off and observe it.
But you can sometimes see those feathered patterns and all that. Yeah. And it's the same thing forming a crystal. So it makes sense that it would have some similarities in the crystalline structure.
Interesting.
That's frost is water. I do want to make a caveat. I mean, we've been talking about crystals and crystalline solids, and I'm not 100% sure if there's like a cutoff line. I think there's kind of a gray area, but most solids are highly ordered. They're just more well-ordered, packed and close together.
Mm-hmm.
But crystalline solids are more ordered than other solids. And I think that's an important distinction to make, that there can be solids that aren't crystals. They're just not as highly ordered. And then very nicely ordered solids are crystalline. If there's an Xray crystallographer out there listening and you know that there's like a cutoff and this is when we call it crystalline versus not, and this is an individual crystal versus a crystalline solid, please hit us up and let us know, because that's an area I'm not 100% sure on, but I just don't want you to think all solids are crystalline.
Got it. So it would be unfair for me to sell, say, this very cheap plastic table and try to upsell it on the internet by calling it crystalline or something. You're saying that I cannot do that.
Yes, that's exactly right.
Okay, good to know.
Let's talk more about how they're studied.
Okay.
So we have the Xray crystallography, and they can actually study snowflakes with those Xray crystallographers that send in the Xray and they bounce off the diffraction, and they can categorize snowflakes. And there are apparently 121 categories of snowflakes as of 2013.
Wow.
That's according to an American Chemical Society video. So that's a pretty trustworthy source.
Yeah.
And they're so beautiful.
That's so crazy. So they just have to have it be pretty cold when they are doing that? Because I think like even just a little bit of time, like putting it on to whatever platform it needs to be on for the Xray to hit it.
Right. I wondered that. And I looked to see if I could find who actually studies them, and I couldn't. I couldn't find like, here's an Xray crystallographer whose whole job is to study snowflakes.
Yeah.
I imagine it would be hard to get funding for that. So I wonder if it's just something they do in their free time. I don't know.
Yeah. Well, maybe if you are already an Xray crystallographer and you do other stuff that makes more sense for the money, and you also happen to be in a place where it snows every year or whatever,
and you can maybe
take
have
advantage.
a chamber that's extremely cold or something. I don't know, but I thought that was really cool.
Yeah, that is really cool.
So if you're an Xray crystallographer out there, or you know one who has taken the crystal structure of a snowflake, hit me up. I'd love to hear from you.
Yeah, absolutely. Like I wouldn't even thought, like they just seem like they don't live very long. Snowflakes. So the idea of studying them other than just trying to take a photo or something seems very surprising.
I do have a picture of a snowflake on my glove. A snowflake landed on my glove, and I was like, you can see everything.
Really?
And I took a picture of it. Yeah, we can put it up for this week's episode.
I think that's cool.
It is so exciting. And then my phone died immediately after I took that picture, so I thought it was gone, and it wasn't.
Nice.
So
this episode brought to you by Apple iPhone. Thanks for being there, even to the last percentage of battery.
To the last drop. It's the same phone that I have now, and that was like 3 years ago. So let's just talk about how old my freaking phone is.
Melissa's a legacy. She's a retro Apple user.
Yeah.
10-year-old computer, 4-year-old iPhone or whatever.
It really is 4 years. Okay. So that's it. That's the basic of snowflakes, that they study them. They use Xray crystallography to study them. And I want to tell you about this cool thing that happened to me while I was studying them. But do you want to tell it back to me first, or do you?
I'll tell it back first and then hear cool thing as a reward.
Yeah, hold on for a cool thing that happened.
Okay. So snowflakes are crystals.
Mm-hmm.
Crystals form from there's a highly ordered structure
Mm-hmm.
and they're really pure
Mm-hmm.
because
Just one substance.
it's one substance and it's forming that like structure as it is, I guess, cooling in every situation.
Mm-hmm. It's as it deposits from any situation I've encountered, as it deposits from the liquid state to the solid state.
Okay. And that's true of all crystals. Snowflakes are also crystals. And their way of doing that is that there has to be something to start with, like a piece of dust or pollen.
Latch on to.
And then as water molecules form on it and cool and freeze, they naturally make that crystalline structure.
Mm-hmm.
But then that thing is continually falling, collecting more water molecules and adding on to the structure as it falls quickly, slowly, as it falls through warmer, cooler air or whatever, and forms a crystal in the air, very small, as it falls to its inevitable death.
That's dark.
And melting once it hits the ground. But the same thing is true of other crystals that form from like a solution like you're talking about. And as it cools, just the substance itself, just the one type of molecule, gangs up. They get together. It's like, oh, hey, we're alike. And that's still so interesting that it just happens that way.
Well, and I can say it happens that way because of intermolecular forces. So and because of the shape of the molecule.
That's why the water is attached to other water, right? I mean, like is attracted to. So as it's falling, it's not like has to do a ton of work to try to get more water to come stick to it, because on the intermolecular level, those hydrogens want to be with more hydrogens.
And that's true for all crystalline structures. The shape of the molecules have different shapes, and the intermolecular forces will dictate what crystalline pattern they take, how they line up with each other. But because that shape is so important to how they're lining up, and the intermolecular forces are so important to how they're lining up, if you throw something else in there, it's going to mess up the whole pattern.
Okay, yeah.
So you don't want impurities.
Yeah.
So a lot of gemstones and stuff that we see are made of ionic bonds, and those form very cool crystalline lattice structures like salt rocks and stuff. But I'm saving that episode. I'm saving gemstones for another episode.
Okay.
But it's a similar process.
Interesting.
I was wandering around the Perot Museum gemstone area.
Wouldn't it be cool if you could sell them for they're as valuable as gemstones?
You'd have to save them though.
Yeah. But hey, it's like you're like, no, this is a smaller one for sure. But it's a beauty and same exact process to some degree. You could try to convince somebody, use all your chemistry jargon.
That's so true.
Be like, this is small. And you'd have to keep it pretty cold, but I'll tell you this, it's 100% unique. So not another gem like this.
So I think your explanation is pretty good. And most of this information came from an interview with a professor at University at Buffalo.
Okay.
And I was reading this interview and it was so interesting. I was taking all my notes. The professor's name is Dr. Benedict. And it was starting to all sound very familiar when I got to this part about a national crystal growing competition. And then I realized the crystallographer who was being interviewed here that I was learning all of this information from is someone that I have actually met.
Really?
Yes, he came to UNT we have seminars every Friday, and he came to UNT for a seminar and talked about some of his work. And the thing that really stuck out to me was he helped start, I don't remember the details, a national crystal growing competition.
Wow.
So any kid can participate. Any school kid, any like homeschool, at school, any child can participate. I think it's under the age of 12 or something, or maybe 16. And they send the kid a kit so that you can learn everything you need to know about growing crystals and try your hand at it. And then you mail in your crystals and there's a competition to see who's the best.
That's crazy.
Isn't that so cool?
That would have been so fun to try to do as a kid.
So if anyone's interested in doing that, it's the U.S. Crystal Growing Competition, and you can just Google that, but we'll also put it in our show notes. And if you have kids or if you are a teacher and you're interested in growing crystals and seeing about growing crystals and trying to learn about that and teach your kids or your students about that, then please, please, please go check that out. The first prize gets $200.
How old do they consider you to still be a kid?
Any student up to 12th grade.
Okay. Dang, that's awesome. That's really cool.
And it's first come, first served basis.
So there's a limited number of entries.
And in addition to putting them in our show notes, we will also try to get them on socials. I'm pretty sure he has a Twitter for the crystal growing competition. So that's really cool. Shout out to Dr. Jason Benedict for your cool work in spreading information about crystals. That's really awesome.
True that.
And that's it. That's the science behind some snowflakes. I love snow. I went to grad school so that I could have snow days, basically. And it hasn't snowed since I started grad school. So here's hoping that this episode means it snows in Dallas.
Yeah, that'd be awesome. It's been a while since there was a serious snow. The other day, it was like a reminder of, what was it, 4 or 5 years ago when that big snowpocalypse happened here. I was in my junior year, I think, of my undergrad, and it was like right during finals time.
Yeah.
So
it was crazy.
It was nuts. Well, dang, that's awesome.
Yeah.
I'm more interested in snowflakes than I was before. I mean, we don't see them super often, so I hope I get a chance to actually observe them soon. Maybe when we are in Indiana, when this episode comes out, I will see some snow.
Hopefully so.
Indiana, if you've ever wanted me to love you, please let us experience some snow when we're there.
And then you can tell all your in-laws about snow.
Yeah. Like, I know you guys are around this a lot, but you don't know a thing. Forget all you know about snow. So Melissa and I have a lot of ideas for topics of chemistry in everyday life, but we want to hear from you. So if you have questions or ideas, you can reach out to us at Gmail or on Twitter, Instagram, Facebook at Chem for Your Life. That's Chem, F-O-R, Your Life, to share thoughts and ideas. If you enjoy this podcast, you can subscribe on your favorite podcast app. And if you really like it, you can write a review on Apple Podcasts. That helps us to be able to share chemistry with even more people. If you'd like to help us keep our show going and contribute to the cost of making it, go to ko-fi.com/chem4yourlife and donate the cost of a cup of coffee.
This episode of Chemistry for Your Life was created by Melissa Collini and J.M. Robinson, and references for this episode can be found in our show notes or on our website. J.M. Robinson is our producer, and we'd like to give a special thanks to A. Collini and In Newell, who reviewed this episode.